So we are continuing with Unit 1, one-dimensional kinematics, and also we'll be looking at continuing in Part B. It's actually near the end of Part B, so after we've covered what is displacement, what is speed, what is velocity, today we're going to talk about acceleration. And that is a big topic that we need to worry about, because this is going to drive a lot of things that we talk about in the next coming months, not just at the end of this month, but also in January, February, March, because after we talk about acceleration, you pretty much use it for the rest of the year, and especially in physics. So it is an important thing. It is a scalar quantity. That's why we see this nice purple arrow there. Not a scalar quantity, vector quantity, I'm sorry. It can be positive and it can also be negative. Okay? However, a lot of times we think that negative is slowing down, but that's not always the case. A lot of times it is, but that's not always the case. And so there can be times where an object has a negative acceleration and is speeding up. It just happens to be maybe speeding up in the negative direction with that. And so all those little components are a part of that, and that's kind of why we have to be very careful on our frame of reference and an idea that we had talked about previously. The equation that we use is going to be this equation here. So I would make sure that you write those in your equation sheets as well. It does have a circle equation in it as well, and that you would have the change in velocity divided by essentially a change in time, which a lot of times isn't going to be very much, if at all. And you would have that, and therefore you can still use those circle equations. Now that sometimes is then written a little bit differently in a circle equation because of the v sub f, the final velocity, minus the initial velocity. Those are going to be things sometimes that we are going to be asked to find. And so we need to be able to know that that's a different part of it. And the reason why I write two different ones there is because if we need to find the final velocity, we can't just blindly cover that and plug everything in. We will have to change the order of operation and be attentive to that order of operation. So we do have to pay attention to those things. We will have a lot of acceleration equations later on in Unit 2, but that's for another time. So let's start trying them out. I think that's probably the best thing to do with some of these things. So a car is moving 50 miles per hour east, then 10 seconds later is moving at 70 miles per hour east. Find the car's acceleration, magnitude, and direction. And so we have to pay attention to some things here. We're going to kind of draw it out, because when in doubt, draw it out is the route that I prefer to take so that we know what's going on. Okay? So if I draw out that we actually don't know how far it's gone in this case, we just know that a car is going at, let's say, 50 miles per hour. We have a time difference of 10 seconds. And so from those two spots, we know that it changes and it's going east here at 70 miles per hour, okay? And we're asked to find what is the car's acceleration with that. And so we have all the parts that we need to kind of put this all together. Now that I have it drawn out, I'm going to resize this so that we can actually now start to write it out. Okay, and that means identifying my givens, and that I have an initial velocity, what's originally going, initial. Sometimes they'll be written as with a 1, but 50 miles per hour. We won't get technical, we'll put the east there. The final velocity is 70 miles per hour east. We have a time given to us of 10 seconds. Now, when we have those things, we also then are told, what is your acceleration? Well, since I have, looking at the equations that we have at this point in time, so far we have speed is equal to distance divided by time. We have velocity is equal to distance divided by, or displacement divided by time. And we have acceleration is equal to v sub f minus v sub I divided by time. Of those equations, we can only use the acceleration equation because that has everything that we need. And it is the only one at this time that has what we want to solve for. So because of that, we take that equation and we're able to take that and go from there. Now, I start plugging what I know into my equation. So I'm going to even get the colors there the same, just like they were from the picture to match up. I don't know what that is. The time will be 10 seconds. The final velocity is 70 miles per hour minus 50 miles per hour. I like to use parentheses so that I remember my order of operation. Doing the next step shows me that my change in velocity is 20 miles per hour. Now that is an opportunity for us to check ourselves. Did I increase in speed? That means my change in velocity should be positive. And sometimes it might be very beneficial to put that sign of what your change of velocity is, so that you remember, oh yeah, it was speeding up. In this case, that's what it was doing in that 20 miles per hour. And so we have that. Now we take that and divide it by the 10 seconds. Those of you that might be able to look at this and say, okay, I can see the zeros are going to cancel out, and I'm going to get an answer of 2. But here's how it's labeled is going to be a little bit different. And that is that it's miles per hour per second. because that's what it is changing. Now, an alternative route could be 2 miles per hour per second would be the alternative way to write it. This is probably the preferred way to write that problem. Because for acceleration, what you're looking at is the rate at which velocity changes. How fast is the velocity changing? Now, when I say fast, a lot of times people think speeding up, but it can also be how fast is it slowing down. Okay, so how fast velocity changes. So here's another example. Bear is running at 4 meters per second north. The acceleration of the bear is 3 meters per second squared. Okay. Another way to write that would be 3 meters per second per second. What is the bear's velocity 2 seconds later? Okay. Since my drawing is sometimes not always the best, I'm going to have just a little bear running at a velocity for 4 meters per second. It's going to accelerate another arrow. And since it's also accelerating north, that's why the arrow is pointing up. There's going to be a time difference such as there. What we want to find out now is what is the bear's, which kind of looks like a little bug there, what is the bear's velocity at this point? What is the bear's final velocity that we have? So I kind of drew it out here. Now, let's solve the problem based on what I have written out. I know that I have a time interval of 2 seconds. I know, I'll keep the colors, try to keep the colors there, that the bear is accelerating at 3 meters per second per second. I also know that the bear is initially going at 4 meters per second. What I don't know is how fast or slow, I guess, the bear is going 2 seconds later. That's what I don't know. So the equation, again, that I have to use is acceleration is equal to v sub f minus v sub I divided by t. Now I have to be a little bit careful in this one because I cannot solve and do the division right away. So this is a good example that we should do. So I'm going to plug the information in, say 3 meters per second squared is equal to 2 seconds minus And that's going to come into play how I would have it written there. So if I want to get rid of the time on the bottom, what would I need to do that? I have to multiply both sides by 2. And I'll change my color here. Okay. Now I can do the multiplication over here, so 2 times 3 is going to give me an answer, and I'm going to change that color because it's going to be different. It's going to be 6. I should change it to a different color. It's going to be 6. Now that seconds that you multiplied it to, it gets rid of, actually mathematically speaking, for those that care, it gets rid of one of those s squares. So actually your new label becomes meters per second. Now we then have another part of that, and that is our final velocity minus our initial, which is 4 meters per second. Now, when we look at this part of it, we can see that order of operations should be very simple now, that to get the v sub f by itself, what am I going to have to do with that -4 to get rid of and have v sub f by itself? So we add 4 to both sides. And what that's going to do is that a -4 and added to a +4 is essentially going to cancel it out. And now 4 plus 6 tells us that v sub f is 10 meters per second. So that one's just a little bit more complicated. However, I think not too bad. We took our time, and that's what's important. So we have this problem here, which is a good one because we have more than one way to solve it, and how you solve it could be a little bit different. So suppose a car is moving in a straight line, steadily increases its speed each second, which means each of these intervals is going to be 1 second intervals. So from when it goes from 35 to 40 kilometers per hour, that happens in 1 second. Then from 40 to 50 kilometers per hour, that happens in 1 second. Then from 50 to 45 also happens in 1 second. So what is the acceleration? Now, one method you could use to solve this problem would be taking and adding all of the accelerations up and then dividing by the total number of accelerations, basically finding an average. So, how does that look? So let's take a look at how this one might be done. So for the first one, we would have 40 minus 35 in 1 second. Then we would add that to final minus the initial of the 40 to 50, that happens in 1 second. Then we would have the from 50 to 45, that happens in 1 second. And so I would be able to solve for that. You say that 5 divided by 1, and then that subtraction would be 10. And then that would be a -5, which would give me 10. Now again, we need to divide that by 3, because it's the whole thing divided by 3, to give me 3.33 kilometers per hour per second. Now that's just one method. The other method would be to go from 35 to 45 over 3 seconds, which then means our final would be 45 minus our initial of 35 to then divide by 3 to give us 10 divided by 3, which again will give us 3.33 kilometers per hour per second. So what this shows is that sometimes there's more than one way to do a problem. Both of them are correct here, but that doesn't always mean that that's going to be the case all the time. Acceleration is a measure of the change in velocity that occurs during that time interval. So in a general statement, that's what we would have. That acceleration is a change in which velocity occurs in a time interval. Or another way of saying, like I've said earlier, the rate at which velocity changes is another way of saying it. It's the rate in which velocity changes. So our labels, as we have seen for acceleration, are usually a velocity over a time, because that is the rate at which velocity is changing. That's that per expression. Now, when the times match up, we saw that we can also have meters per second squared. We have also done the rate at which velocity changes, kilometers per hour per second. So the labels for acceleration all basically tell us that we are talking about the rate at which velocity changes. Now, what's wrong with these statements? First one, acceleration tells us how fast the object is moving per second. What's wrong with that statement? So with these statements, acceleration tells us how fast the object is moving per second. It can be other time intervals. It could be whatever that may be. Acceleration can be increasing or decreasing, depending upon what's happening. Here would be an opportunity when we see the object going up the ramp. So the numbers tell us that this object is slowing down, but what is the acceleration? The acceleration is 6 minus 9 divided by 2, 3 negative, actually, divided by 2. And you would have an acceleration of roughly, what, 1.5 with that. So if acceleration is equal to a negative 7 meters per second, is it speeding up or slowing down? This is a difficult question because a lot of us would automatically want to say slowing down. However, if it is accelerating in the negative direction, you're going to have a negative direction divided by time, which will give you a negative velocity. Now, if it still is moving in the negative direction and has another negative velocity greater than the initial velocity, you are still going to have a negative acceleration. So you don't know if this is actually speeding up or slowing down based on just the number. So what we would have to say then is more info needed. So maybe as an example of a lab that we've done before is that now the object is moving down the ramp where now it has a negative acceleration or negative velocities because it's moving in the negative direction. So our initial final minus the initial for this case would be a minus divided by 2, which would be 9 plus 6, which would be a negative 3, divided by 2, which tells us that it has a velocity of somewhere around 1.5 meters per second in the negative direction. So here we have a negative acceleration and the object is speeding up. So what does that mean? That means it's going down or away from the detector in that negative direction. Probably accelerating due to gravity, which is negative. So what we need to really point out is that an object speeds up when its velocity and acceleration have the same direction. And this is a big point. It's the same direction. Okay? An object slows down when the velocity and acceleration have opposite directions. So it all depends upon the direction that the object is moving. So make sure when you're drawing them out that you use your arrows to draw out what is happening, because it's all about the direction that the object is moving.